Hi, now we have an example for quasi-binomial model. So we use the library, the faraway, and we use the mammal sleep data. So this is the data for 62 species of mammals, and it may demographic information such as the body weight, and the brain size, and the non-dream hours of sleep, and the dreaming hours of sleep, and the total hours of sleep, and also the lifespan of that animal, and the gestation and the predation. So how fragile as a for the predation, or the how much exposure for the risk, or and so on. And the our objective is the how much the dreaming sleep the animals have out of the all total the sleeping hours. So you can see the some NAs, but actually the most data points have the numbers, and you can take the proportion such as 2 over 8.3 or 1.8 over 3.9 and so on. So we think about the dream over sleep, dreaming sleep over the total sleep. So we want to explain this by, so we exclude this, but there are other variables. So that is our objective. So here, even the sleep and the dream are not integers, so it's fractional numbers. So this is proportion, but not necessarily binomial, the random variable, because we don't have m here. But still, the quasi-maximum likelihood estimation applies, because as if this follows the binomial distribution with dispersion parameter. Okay, so the R code. So at first, we think about the proportion, the dream over sleep with this data set. And we define this as the PDR, because this is sleep also is called the paradoxical sleep. And okay, then the model, the GLMQ, that is the GLM, still we use the GLM function and the response variable and all predictors. Then family is equal to quasi-binomial, then the data set, mammal sleep. So that is the code for quasi-binomial model. Yeah, so we don't really have the output yet, but also that we can calculate the F value. So what happens when we drop the one predictor, is that significant or not? So if we drop some variables, that we can see whether or not it's significant. Okay, so this is the full model. And what happens if we drop the body weight? Then actually the p-value is 0.04. So of body is significant factor. But some variables are not necessary, probably. For example, if we drop the predation, this variable, probably this is similar to exposure or danger. So this isn't very useful. So we can exclude this variable first. And we repeat this to get the best model. So basically, we have the redundant predictors here. So we drop one by one to make it it's no longer possible to drop insignificant variables. And it seems all variables are insignificant except for log of body. But if we drop a few variables, some other variables becomes significant. And here, the step function does not work. Why? So basically, this is quasi-maximum. So the AIC does not exist because this is not maximum likelihood estimation. But on the other hand, we use the F-test. So we also rely on some, maximum likelihood estimation. So it's not clear why drop one works and the step does not work. But at least maybe the F-test is a little more accurate than chi-square test. So this result is a little more accurate than using step function. So that is the reason that step function does not work. Okay, so we have to manually drop one variable by, so one variable at a time. So we drop the predation at first. Then after that, finally, we will get this as the final model. So the PDR, the paradoxical sleep ratio on log of body, log of lifespan, and danger. So actually, these three variables are all significant at 5% level. And this is the output, so we don't have AIC. And still, we calculate the null deviance and residual deviance based on the quasi-maximum likelihood. And we got the estimate and the standard error, the t-value, and so on. Yeah. And also that we can have some residual plots. So sorry, diagnostic plots. So at first, this one is the Cook's distance. So Cook's distance measures how influential each point is. And actually here, the Asian elephant, probably this is around here because the elephants have the very large weight. So this point may be too influential compared to other points. And maybe some other points are too influential compared to these points, but at least maybe it's useful to see the result, estimation result without Asian elephants, and also maybe estimation result without maybe these 4 or 5 observations. And the right pane is the Pearson residuals and the log of body. So in general, the residual plot, it's useful to put some predictor here, maybe x sub I, and the Pearson residual. This is the standardized residual defined in section 3.2. So then we can get this. So if we have entirely random figure, then that's fine. But if not random, then we have trouble. It's not clear if it's entirely random or not. Maybe some people claim that maybe some curvature here, maybe around here, the smaller values, around here, larger values, and larger values. So maybe some curvature, but not entirely clear, especially if we drop this. So we can check the residual plot. If we have specific pattern, there's still that we have room to improve. And these are the figures. So at first, we drop some observations with NAs. So for regression model, all variables should be available for observation to be used. And this NA.omit function basically drop all rows with NAs. One or more NAs. So we just pick up the response as well as the predicted variables 1, 6, 10, and then we can drop the NAs. Then we make a half normal plot of the Cook's distance of this model and the label. So that we use the row names as label so that we can see the name of animals. And also the residual plot. So we put the predictor and the residual, the Pearson residual, that is standardized residual. So yeah. So I think the textbook uses the fitted value for this one, because if we have multiple variables, maybe fitted value is the representative one, but it's not clear what that means. The best way is the predictor versus fitted residual, sorry. Yeah, and AB line 0, 0, add the line of y is equal to 0. Yeah, so this is the example, the R code example for quasi-binomial. And the code is not much different from usual GLM, the binomial, the binomial regression model. The only difference is the family is quasi-binomial. And the dispersion parameter is here, the 0.04. So so in general, you can see that the variance of y is equal to p times 1 minus p over n. But here we don't have any number of observations here. So we only have the proportion. So n is ignored. So that's why we have very small value. So basically this corresponds to 1 over n. So also the n does not mean anything here. So that's why that we have very small the dispersion parameter.